Welcome to the Flyback Design Tips and Tricks presentation. My name is Moritz Müller and I am an applications engineer at Texas Instruments. I will start this presentation with the basics of the Flyback topology. I will give an introduction of the Flyback converter and give an overview of the most common Flyback applications. Then I will continue with a Flyback power stage design example. We will go through the steady state analysis and after this do a step-by-step design example. I will end this presentation with a conclusion. Let's start with the basics of the Flyback topology. What is a Flyback converter? A Flyback converter is a switch mode converter that can be used for both DC-DC or AC-DC applications. The power transfer happens during the switch off time. It can be used in low to mid power ranges and it uses a coupled inductor as an energy storage. With a Flyback converter, isolation is possible. It can operate with a wide input voltage range and the output voltage can be higher or lower than the input voltage. A high conversion ratio is possible with a Flyback because of the transformer's turns ratio. It is a low-cost topology and can support multiple outputs. Let's continue with the most common Flyback applications. Flybacks are often used in offline applications like phone chargers. Here the isolation as well as the high conversion ratio is important. Also, Flybacks are used in traction inverters for automotive. Here they are commonly used as isolated bias supply. They operate over a wide input voltage range from 40 to 1000 volts. Also, you can find Flybacks in onboard chargers or in power over Ethernet applications. The Flyback topology can be derived from a simple inverting buck-boost topology like shown in the upper left corner. First, the inductor is replaced with a coupled inductor. Now the galvanic connection is split up, the high side switch is moved to the low side for an easier control. If now the schematic is redrawn, the result is the known Flyback schematic like shown in the lower left corner. The output voltage can be calculated with the formula shown in the middle. It can be higher, lower or equal the input voltage. The turns ratio N2 to N1 allows a very high conversion ratio. The transfer of energy in a Flyback converter can be divided into three phases. When the FET is turning on, the voltage across the primary magnetizing inductance equals the input voltage. A current is building up through the primary inductance. In this phase, energy is stored in the Flyback transformer. It is a function of the inductance, the duty cycle and the cycle time. During this phase, the secondary diode is in blocking state. When the switch is turning off, first, the energy that is stored in the leakage inductance will be absorbed by the clamping circuit. We will go more into the details later. When the switch turned off, the stored energy is transferred to the output through the diode. In case of DCM operation, all the stored energy is transferred. A Flyback has a pulsating input and output current. Like other topologies, also a Flyback converter can operate in the continuous conduction mode, called CCM, or in the discontinuous conduction mode, or DCM. In continuous conduction mode, shown on the left side, the current through the inductor never reaches zero. In DCM, the current will go to zero in every switching cycle. As you can see from the formulas, in CCM the duty cycle is only dependent on the input voltage, the output voltage and the turns ratio. In DCM, however, it also depends on the output current and the inductance. Both operation modes have advantages and disadvantages. One advantage of the CCM is the smaller ripple and RMS currents compared to the DCM. Also, the FET's conduction and turn-off losses are smaller. Because of less ripple current, also the inductor core losses are lower and there will be less capacitor current ripple. In CCM, you can achieve a better full load efficiency and there are less EMI problems and also the EMI filters can be smaller. In DCM, one advantage is that there will be no reverse recovery losses in the diode. The inductance value will be lower and this allows to use a smaller transformer. In DCM operation, there is no problem with the right half plane 0 and in current mode control, there is no slope compensation needed. Also, DCM allows a better load step response compared to CCM. The right half plane 0 was mentioned already in the slides before, but what is it? The right half plane 0 exists in topologies where the energy is delivered to the output during the off phase of the switch. When there is a load step, the output voltage will drop. The reaction of the controller will be to demand a higher duty cycle. A higher duty cycle means a shorter off time, so in the first moment less energy can be delivered to the output. This will let the output voltage drop further. So the effect of a control action during the on time is delayed until the next switch turning off. This means the initial reaction of the controller is in the opposite direction. This is the right half plane 0. It causes a phase decrease with an increasing gain. This we cannot compensate, so the right half plane 0 has to be avoided. A rule of thumb is to cross over latest at 1/5 of the right half plane 0 frequency. The formula to calculate the right half plane 0 frequency is shown in the lower left corner. Any transformer, in the current application the Flyback transformer, has some leakage inductance. There is no perfect coupling between the transformer's windings. It is always a compromise between parasitic capacitance and leakage. Better coupling means less leakage, but a higher parasitic capacitance. Looking at the physical construction shown, we can see that the primary winding is the closest winding to the center gap. The leakage inductance is represented as a single inductance, L-leak2, located in series with the secondary winding, which is the farthest from the center gap. So when the main switch turns off, L-leak2 opposes to any increase of the secondary current, IS, and any decrease of the primary current, IP. At the same time, the magnetizing inductance, Lm, works to maintain the total magnetizing current. So there is a transition from primary to secondary, and during that time there's a voltage spike at the drain of the primary FET. The clamp circuit is used to limit this voltage spike to protect the FET. The rate of rise and fall of the current on each side is influenced by the leakage inductance. Note also that a higher clamp voltage means a faster commutation from primary to secondary. On the left side of this picture, the waveforms of a low clamping voltage are shown. As you can see, the voltage at the FET is limited to a low value. However, the commutation time from primary to secondary is quite long. This means higher energy loss. If a higher clamping voltage is allowed, like shown on the right side, the commutation will happen faster. The effects of a transformer's leakage inductance are that there will be clamping and snubber circuits needed to protect the primary FET and the secondary rectifiers. Also, it causes a lower power supply efficiency. If a synchronous rectifier is used, the leakage inductance also influences the gate drive strategy. The duty cycle as well as the magnetizing current are higher than expected, and also the H-field radiations are higher. The leakage inductance also impacts the cross-regulation when using multiple outputs. Putting the transformer's windings closer together improves the coupling and reduces the leakage. However, this also means a higher parasitic capacitance, which can cause EMI problems. So this is always a trade-off. The graph on this slide shows the lost energy for different leakage to magnetizing inductance ratios over the clamping voltage. To minimize the losses, it is a good practice to clamp at 1.5 times the reflected voltage. Like mentioned before, the leakage energy is absorbed by the clamping circuit during the commutation from primary to secondary. R snub 1 dissipates the leakage energy. The clamp capacitor C-snap ensures a low voltage ripple and R-snap2 damps the ringing. It is important to use a short connection with minimum loop area in the layout. V-clamp will be at the maximum at full load and at minimum input voltage. It is a trade-off between efficiency, peak drain voltage, output current limit and cross-regulation. In this slide, the two most common clamping circuits are shown. On the left side, the RCD clamp, like shown in the slide before. It is cheap, but needs more design effort. On the right side, you can see the ZD clamping circuit, using a Zener diode. This circuit is easier to design and has a lower standby power dissipation, but it is more expensive. A detailed design guide is available under the link. Here you can see the datasheet of a standard flyback transformer. It is important that it is labeled as flyback transformer, because normal transformers don't have an air gap, which is important for storing the energy in a flyback. Other important parameters are the primary inductance, the turns ratio, the saturation current and the leakage inductance. These values are all listed in the electrical properties. Also, it is important to check the schematic, so that the windings can be connected with the right polarity. In order to understand how the current limit works, we look at the flyback power supply operating with peak current mode control in CCM. As shown in the picture at the left, we see a flyback circuit with slope compensation connected to the current sense node. This is compared with a reference signal coming from the error amplifier after having been divided. This reference signal is also limited to a maximum VC_lim, defining the peak current limit. The upper timing diagram shows what happens when the peak current limit has just been reached. I peak lim corresponds to VC_lim. Also note that the output current corresponds to the average output current of the secondary side. The lower timing diagram represents what happens if a short circuit is applied. In that case, the output voltage goes close to 0 volts, which means that the downslope of the secondary current goes down, the duty cycle becomes very low, and the output current becomes much higher than just at current limit. When we look at the basic equations of the peak current control for flyback, we can see that as the input voltage increases, the duty cycle decreases, while 1 minus the duty cycle increases. What does this mean? For fixed peak current limit VC_lim, the output load current limit increases when the input voltage increases. In other words, at the point at which the current limit has just been reached, the output power available to the load becomes the maximum at the highest input voltage. This graph illustrates the fact. In that example, the load current available before reaching current limit increases by close to 50% as the input voltage increases from 22 volt to 57 volt. This means the worst case maximum stress on the power components is at maximum input voltage. This dependency on the input voltage can be almost eliminated by using a simple feed-forward technique. In the schematic, RFF is used to inject this feed-forward signal, which is proportional to the input voltage on the current feedback node. The graph shows that by using feed-forward, a quasi-constant power limit can be achieved. As the input voltage increases, the output load current limit varies from 5.6 to around 6 amps. This provides a better control with less stress on power components during overloads. For example, by using feed-forward, the primary peak current during an overload or short circuit reduces dramatically when at maximum input voltage. This means less leakage energy at maximum input voltage and less voltage stress on the primary FET. This even means that in some cases the clamp circuit can be redesigned to be more efficient while keeping the FET safe. By using a feed-forward, the cost and size of the converter, including the power transformer, can be reduced. And also using feed-forward can be used to improve the line noise rejection. Let's continue with the second part of the presentation, the flyback design example. This slide gives an overview about the steady-state analysis of a flyback converter. The formulas here will also be used for the following calculations. The following design example refers to the PMP 40555 reference design. You can find this design online, and it's a wide input range, high-efficient flyback converter for IP camera and line-powered video doorbell applications. The input voltage range is from 9 to 60 volts with an output of 12 volts. The output current is 2 amps, so the output power is 24 watts. The switching frequency is 250 kHz and LM51551 is used as a controller. For all calculations that are done in the following design example, also TI's Power Stage Designer can be used. It is a Java-based tool that allows calculations for 21 power topologies. It can be used for calculating the power stage, the loop, load steps, losses, filters, and snubbers and clamps. In addition to the normal calculation, I will also show every design step with the Power Stage Designer. The Power Stage Designer can be downloaded with the link on the slide. The first step is to decide for an operation mode. As explained before, both operation modes, CCM and DCM, have advantages and disadvantages. In this example, we decide for CCM operation mode over the whole input voltage range. The next step is to set the switching frequency and the maximum duty cycle. The switching frequency of a flyback converter is normally in the range of 50 to 500 kHz. In this case, we decide for 250 kHz. A maximum duty cycle of 50% is a good target when designing a flyback, because this maximizes the conduction interval for both the primary and the secondary. But also higher values are acceptable. For the worst case, we allow a duty cycle of 65% in this case. To prevent core saturation, the volt-second product for the on and off times must be balanced. From the volt-second balance requirement follows the maximum turns ratio primary to secondary to stay below the maximum duty cycle of 65%. In this case, it is 1.34. On the right side, you can see how this calculation is done in the Power Stage Designer. The design values are entered in the fields, and the Power Stage Designer will recommend the turns ratio for the transformer. Here, marked in yellow, it shows 1.32. The next step is to calculate the required minimum primary inductance. This can be done using the formula shown here. When the output power is low enough, the flyback will switch from CCM to DCM operation at a certain point. When we set this point to 20 to 30% of the maximum output power, in this case 5 watts, we will get a minimum inductance value of 12.3 microhenry. In the Power Stage Designer, you can click on the FET symbol to see the current waveform through the primary inductance. With the sliders, the input voltage is set to the minimum. Then the output current can be reduced with the other slider until the current waveform shows the transition from CCM to DCM. Now a suitable flyback transformer has to be selected. In this case, we choose a Wirth off-the-shelf transformer with a primary inductance of 14 microhenry and a turns ratio of 1.33. The leakage inductance is 300 nanohenry, which equals 2% leakage inductance. Now, as we decided for a transformer, the minimum and the maximum duty cycle as well as the peak primary current can be calculated. In the Power Stage Designer, this can be simply done by entering the chosen inductance value and by clicking on the FET symbol. For the minimum input voltage, the tool will show the maximum duty cycle. For the highest input voltage, it will show the lowest duty cycle. The minimum duty cycle in this example will be 21.7%, the maximum duty cycle 64.8%. The calculated peak primary current will be 5.1 amps. As the next step, the maximum drain source voltage needs to be calculated. It is the input voltage plus the voltage that is reflected from the secondary to the primary side according to the turns ratio. In this case, we expect a maximum drain voltage of around 77 volts. We add some margin and choose a 150 volt rated FET. In the power stage designer, the maximum FET voltage will be shown by clicking on the FET again. Now a diode needs to be selected. For this, the maximum reverse voltage and the average forward current needs to be calculated. Some margin is added and then a suitable diode is chosen. By clicking on the diode symbol in the power stage designer, the maximum reverse voltage and the average forward current will be shown. The power stage designer also offers a convenient possibility to estimate the FET and the diode losses. To calculate it by hand, you can follow the formulas shown on this slide. Knowing the losses is important to choose the right package size or to use a heatsink if necessary. Now the current sense resistor needs to be selected. The overcurrent protection should not be triggered in normal operation. Smaller resistor values reduce the power losses, but they increase the noise sensitivity. Also, too small resistor values can lead to inductor saturation and/or circuit damage during an overcurrent fault. LM51551 has a 100 mV peak current limit threshold, so 7.5 milliohms are used as a sense resistor. The losses in the sense resistor will be around 100 milliwatts. The last step is to calculate the clamping network. A detailed guide with formulas can be found on the linked page. The Power Stage Designer also includes a calculation tool under the menu RCD Snapper Calculator for Flyback. There are different ways how to close the loop with a flyback converter. There are primary side regulated flybacks, which can regulate the output by sensing the reflected voltage at the switch node. There is no need for an optocoupler then, and the accuracy is good. However, the cross-regulation is bad. It is also possible to have a PSR flyback that uses an auxiliary winding to regulate. This needs an additional winding, but also no optocoupler. The accuracy is not good and also it's very load dependent. For a secondary side regulated flyback, an optocoupler and an external reference, mostly the TL431 is needed. This offers the best accuracy of around 1%. Here you can see the final schematic of the example we just calculated. The loop in this case is closed using an optocoupler and the TL431. At the last point I come to the conclusion. When is a flyback topology a good choice? It is a good choice when isolation is needed, when there are very wide input voltage ranges, or very high transfer ratios are needed. Important design parameters are the operating mode, like explained CCM or DCM, the switching frequency, as well as the transformer specs. The Power Stage Designer is a very helpful tool for designing a flyback. With this, I would like to end my presentation and thank you very much for your time.